Hello there. So today we are going to talk about correlation. And specifically, we're going to talk about what's called our R value. We are going to find the R value using the calculator, and we are ultimately going to learn how to interpret this R value. So let's get started. Okay, so before we actually really get into things, if you haven't done this already, you're going to need to do some setup on your calculator. So get out your calculator and follow this process. So when you hit second catalog, it's basically a long list of like all these different functions that you can do. If you hit the alpha D, it'll kind of take you down to the D's. You need to get to diagnostic and turn the diagnostics on. So rather than just scroll a million times, hitting the alpha D is going to be a little quicker way to get there. And all this does, you really just need to do this one time, and then the diagnostics kind of stay on until your calculator gets reset. So if your calculator ever gets reset, you might have to repeat this process, but otherwise you won't need to. All right, let's talk about correlation. So correlation, and specifically our R value that we're going to discuss, is going to talk about the strength and the direction of a linear association. And so the important part here is that correlation, the way we're going to discuss it, or the correlation that we're going to discuss, is only applicable to linear association. So what does that mean? It means that you should have an indication of a linear relationship before you even look at correlation or talk about correlation. So in other words, make a scatter plot first, check that scatter plot, make sure it looks linear. So again, correlation is going to tell us two things, the direction and the strength of the association. All right, so here's some properties of correlation, or in other words, our R value. It's always going to be a number between -1 and +1. And if we have a positive association, so in other words, if my scatter plot kind of looks like this, that R value is going to be a positive number. On the other hand, if my scatter plot has a negative association, that R value is going to have a negative number. So if my R value is -1 or +1, that's only going to happen if the points on my scatter plot are in a perfectly straight line. So this R value would be 1, or if my line had a negative slope, my R value would be -1. So in reality, in real life, that is not going to often happen. We're not often going to have real life data that falls on a perfectly straight line. So you might see some R values like 0.99 or 0.98 or -0.98 or 0.97, things like that. That's about as good as you're really going to get in reality. So with that being said, the closer the R value is to 1 or -1, the stronger the relationship is. And if the relationship is weak, the correlation is going to be closer to 0. And so here's just kind of like a general guideline scale for your terminology, when you talk about how strong the relationship is. Typically, if our R value is between 0.8 and 1 or -0.8 and -1, we say it has a strong relationship. Moderate would be between -0.8 and -0.6, or 0.6 and 0.8. And then anything in between -0.6 and +0.6 is like a weak to no relationship. And I just want to draw you a rough sketch of what that would look like. So keep in mind, if there's a positive association, as X increases, Y tends to also increase as well. And it doesn't mean that it's a perfect relationship, you know? So sometimes, like if I look at this point versus this point, in this point, X has increased, but Y has actually decreased, right? But overall, the general trend is that there's that positive trend. When we say there's weak to no relationship, it means that as X kind of increases, I can't make a prediction about Y. So Y could sometimes increase, Y could sometimes decrease, right? So basically my points are kind of more like randomly scattered. Okay. So here's a couple examples of what scatter plots might look like that have each of these R values. So take a look, even at like this one right here, the correlation is negative, meaning that there's a negative relationship. And I do kind of see these points like trending down, but how strong is that relationship? It's not very strong at all. Like the points are very far away, typically, from that red line that I drew. As opposed to, let's look at like this one here. If I were to draw a line that I would say is kind of like in the middle of the data, and this is not perfect, but all of those points are really close to that line. So my R value is way closer to -1. And then you can see some kind of things that are like in the middle. So I would say like this is a strong, positive, linear relationship. This one here has a strong, negative linear relationship, as opposed to this one here that has like a moderately strong negative linear relationship. Now, I gave you this cutoff, these guidelines back here a second ago. Think about it this way. If I had an R value, if I had a scatter plot with an R value of like 0.8, technically according to this, I would call that a strong positive linear relationship. Well, what's the difference between that 0.8 and like a scatter plot that might have an R value of 0.79? There's really not going to be a difference. So these cutoffs are kind of a little bit vague, but or I shouldn't say they're not like exact like lines in the sand, you know. But this is generally where we should be with our strength, with naming our strength. Okay, so a couple things that we should keep in mind. Correlation does not imply causation. So because two variables are correlated does not mean that one causes the other to change. So for example, if we looked at someone or in a high school, seniors, let's say, people's SAT scores versus their ACT scores, I would say we would probably have a pretty strong correlation. As SAT score goes up, typically the ACT score would go up as well for the individuals, right? But that doesn't mean that one causes the other to change. Correlation doesn't measure form, and we'll see more what I mean in just a second, but essentially to find these R values, to find that correlation, it's just a formula. So I could theoretically have data that when I make my scatter plot, it's clearly nonlinear. And you'll see, but you could plug these points into the R value and get an R value. It might be like 0.3 or point whatever, but that R value alone is meaningless because this data is not linear. So in other words, correlation doesn't measure the form. It should only be described, or I'm sorry, used to describe linear relationships, and it's not a resistant measure of strength. In other words, it is affected by some extreme observations, and you'll see why in just a second. So here's the formula for R, although you should not have this memorized by any means, and you really probably are never going to need to use it in an AP statistics course, but it's interesting to kind of look at and think about, well, where does R come from? And also, we can see some of the properties of R that we talked about and that we will talk about in a minute, kind of from this formula. But look, this formula looks a little crazy. But basically, here, if I have a scatter plot, essentially what I have is a set of X and Y coordinates, right? So maybe -2, 6. All right, so maybe just like, and I'm not going to go through calculating it, but just as an example, okay? I have my data points, and when I plot them, this gives me my scatter plot. In order to find the R value, what you would do is you would kind of like isolate the X values from their Y values. And you would say, well, let me just look at these X values. Let me find the mean of all the X's and the standard deviation of all the X's. In other words, what's the mean of these three numbers, -2, -3, -2? And then what's the standard deviation? And then I would calculate, look here, I would calculate a z-score. This is my z formula. It's like value minus the mean over the standard deviation, right? So I'm essentially calculating a z-score for each individual x value. So relative to the other x values. And then I'm kind of isolating the y values. I'm calculating the mean of these y's and the standard deviation of the y's. And then I'm calculating a z-score for those individual y values. And so then I would take, essentially, I would regroup these that go together as a point, and I would say, all right, well, what's the z-score for this x value? What's the z-score for this y value? Let's multiply them together. And then the z-score for this x and y, multiply them. Z-score for this x and y, multiply them together. Add them all up, that's that summation, right? And then average them out, basically. What's the average? But in this case, remember, degrees of freedom. Because our data is going to come from a sample most of the time, we aren't going to divide by n when we take our average. We're going to divide by n minus 1 because of that idea of degrees of freedom. But listen, like I said, you don't really need to know this formula necessarily, but what I do want you to understand is that in order to calculate our R value, we basically standardized all of our data, all of our X values and all of our Y values. So if we standardize our X and Y values, we no longer have units. So if these are like shoe sizes versus heights or something like that, shoe sizes are measured in terms of, what are they measured in? I guess shoe sizes, I don't know. But heights are measured in terms of like inches or feet or whatever. We no longer have those units. And that's going to come up in just a second. Okay. So here are some additional facts about correlation. Number one, both variables have to be quantitative. In other words, numerical. Think about it. Could I come up with an R value for like hair color versus age? Hair color versus age. Well, hair color is like brown, black, red, blonde, whatever, right? I can't come up with a mean and standard deviation for hair color, so I can't come up with a z-score, so I can't come up with an R value, right? So both variables have to be quantitative. And correlation, that R value makes no distinction between explanatory and response variables. Going back to the formula. So, right, we said, think about how this is calculated. We take the mean of all the X's, the mean of all the Y's, and standard deviation as well, calculate the z-scores, multiply them together. Does it matter what order I multiply these in? Could I have multiplied like the X z-score times the Y z-score, or could I have reversed it? It doesn't matter. I'll still get the same thing. So in other words, it doesn't matter what's my explanatory and my response variable, or I could like flip them. I would get the same R value regardless. R does not change when we change the units of measurement. So for example, I think one I just used was like if I looked at like shoe sizes versus people's heights. If I measured the heights in feet, and I calculated an R value and I got like 0.7. And then I changed all those units to inches and I calculated an R value, I would still get 0.7. And again, because where did the R value come from? It's from standardized scores. So if I change units, I'm changing units on everyone's heights. So I would still have the same standardized scores for each, height value. We talked about this. It has no unit of measurement. It's just a number. So it would not be appropriate to say like, oh, my R value is 0.7 inches. Okay, let's do a little practice. So here's a scatter plot. It shows the 40-yard dash times in seconds and the long jump distances in inches for a class of 12 students. So take a look at the scatter plot. Make sure you understand what you're looking at. Now, they tell you, or I'm telling you, that the R value for this scatter plot, for these data, is negative 0.838. Interpret this value. So first of all, if I'm asked to interpret an R value, I should always think, let me double check, is the data linear? When I look at that scatter plot, it appears to be linear. So yes, it's okay for me to go ahead and interpret this. So my interpretation would be something like this. There is a strong negative linear relationship between the 40-yard dash time and long jump distances for these 12 students. So that's my interpretation. Let's go through and talk about it. Most importantly, because this is the part, I say most importantly because this is the part that is often forgotten, I have context. So this is my context, right? Anytime you're interpreting, you have to have context. If you don't, you're going to lose credit. What does R tell us? We assume that it's a linear relationship, and we check that. And it tells us about the strength and the direction. So you're going to have like strong or moderately strong or weak. And then you're going to either have the word negative or positive. And we are always going to have the word linear. Because if it wasn't linear, we wouldn't be interpreting it. So if my scatter plot didn't look linear to begin with, I would write something like, it's not appropriate for me to interpret this R value because the data is not linear. Okay, so last but not least, we are going to use our calculator to find the R value. So if you don't already, make sure you have some data in your calculator. I have random data in my calculator right now in L1 and L2, but if you don't have anything in there already, you can just put anything in, okay? So just here's a caution. If you're just making up numbers, just make sure you have an even number of numbers in L1 versus L2. So if you don't have anything, you could do like 1, 2, 4, -5, let's do like, I don't know, 2, 0, okay? So you're just going to put that data in if you didn't have anything else in your calculator already. So watch, ready? I'm going to X out of here. I'm going to go to my calculator. Stat edit is where I would enter my data if I didn't have something in already, but I'm going to go check. If I go to the bottom of L1 and L2, it looks like I have some data in here already. So I'm going to go second quit. And now I'm back to the home screen. In order to find my R value, I am going to go to Stat, Calc, and then Lin Reg down here, option 8. So I can hit 8, or I can scroll down and hit enter over 8. Now I can change what data I want to put into like my list 1 and list 2. I'm sorry, into my X list and my Y list. In this case, I'll just use L1 versus L2, but if my data were in like L5 and L6, I could change that. And then I'm going to scroll down, hit calculate, and when I do, the rest of this we're going to interpret later, but it essentially gives me my least squares regression equation, R squared. We'll talk about that later, but here's my R value. Here's my correlation coefficient. So that 0.748, that's my correlation coefficient. Now, before I interpret this, remember we said that we should make sure that the data is linear to begin with. So if I'm a good statistician, which I am, I'm going to go and make a scatter plot. And this was L1 versus L2. So I'm going to zoom 9. There we go. So that's the data that I just so happen to have in L1 and L2. And if I look at this, I mean, I know we just saw the R value, but I would probably say that there is a positive, relatively linear relationship here. And if I'm looking at this, I'm kind of thinking, I'm not sure about the strength. It's definitely not like super strong. I know that my R value is not going to be very close to 1, but how strong is it really? That R value is going to help you make that decision. So going back, let me run through it again. Stat, calc, option 8. I have L1 and L2 in there. Hit calculate. Okay. So that R value is 0.748. And so that kind of confirms, if I had to interpret this, I would say that the relationship between X and Y in context, and I don't know what those values are, but this would tell me, this R value would tell me that there is a moderately strong positive linear relationship between these two variables that I'm looking at. Okay, that's all I have for you today with correlation. Thank you so much for watching.